So I will be presenting joint work with AofA24, who is a PhD student of Michael Tromata. And the problem was brought to us by Laurent Ménard and Nicolas Curien. We are going to look at large matrices and their spectrum, so their eigenvalues. And there are a bunch of applications for that, well, a lot of them. There's application in wireless communication, compute the capacity of some channels when you have antennas and several antennas on both sides, receiving and emitting, transmitting. You can think about that also to reduce the size of the matrix, taking into account only the space corresponding to the highest eigenvalues, or you can use that for clustering. But to be honest, what I will present to you today is a bit more fundamental and far from those applications. But yeah, just so you know, they exist. So we'll be looking at large GNP graphs. So this is a graph with n vertices. Every pair of vertex is linked with an edge with probability p. And we will look at the adjacency matrix, which is the 0, 1 symmetric matrix representing it. So when looking at the spectrum, we need a way to represent this set, right? And one that has proved very productive is the empirical spectral distribution. So this is this sum here. So to give you an idea of what it is, I took the x-axis. I put bins on it of same width, small width here, 0.2. Why not? So I divided it like that. And then I took a large matrix, size 200, coming from, a GNP model. And I count how many eigenvalues fall in each bin. And if you draw that, they end up forming a rescaled circle. So that's the famous semicircle law of Wigner. There is one point that always tries to escape, but because of this division by the number of vertices n going to infinity, well, it dies. It doesn't influence what is happening here, and it doesn't influence this convergence here. So that's a very famous result. And GNP is a case where the graphs typically contain a quadratic number of edges. So the next, maybe a natural question is, what happens when the number of edges is linear? What happens when we look at GNP, but with P equals C over N for C constant? And it has been proven by those authors that indeed, again, we have a convergence. But the limit is a bit stranger. So something I should say is that because the matrix here is random, this distribution here is random. So we often think about random distribution as giving us the distribution for random variables. But what I mean here is that it's really the distribution itself is random, not representing a random object, right? But the limit, turns out, is not random. It's deterministic. So that's the kind of the surprise in the result of Wigner. And in the sparse case, so P equals C over N, we have the same behavior, but the limit is way stranger. It was a half circle before, and now, well, we don't really know much about it. So some results exist, but for example, the atomic part, so the points with a positive mass, in this distribution, in the limit, is dense in R. So that's already, it's, I see that and I'm thinking, how am I going to study this, right? I don't have the tools. I'm in analytic combinatorics. I like, analytic functions. They are nice. They don't do that. So we follow the idea of Bauer and Golinelli and Enriquez and Ménard, and we try to add a few steps after them. And the idea is to look at the limit when n goes to infinity first, and then at what happens when C is large. So we saw in the talk of Michael yesterday that to investigate distribution, a good idea is to look at the moments. So it was actually what Wigner did. He looked at the moments of his law, the empirical spectral distribution. And so the odd moments tend to 0, the even moments tend to a Catalan number, and the Catalan numbers, the only law with moments, the Catalan numbers, is the similar circle law. So that was his proof. So we do the same here. And actually, it was done before. And when we take the limit when n goes to infinity, we find, again, the Catalan number. So we're very happy. But actually, it's very different from what is on top. On top, if you look at error terms, it will be error terms in n, right? But on the bottom, we only keep on n the first term, the main asymptotics. And then we make expansion with respect to C for C large. So those are two very different things, up and down, just to avoid any confusion on that. All right. So a big question for many of you probably is, okay, I talk about the spectrum of random graphs, but also in the title, there was 3 walks. So what's the connection? So when we look at the nth moment of the law, well, it's the sum of eigenvalues at the power L, which can be rewritten as a trace of the adjacency matrix at the power L. And this is very nice because we have a combinatorial interpretation for that. This is walks, closed walks, so starting and ending at the same point of length L. And the probability that such a walk actually is in a graph, because of the GNP model, it's the product of the probability that the edges are there. So it's a C over n, the probability for any of those edges, at the power the number of distinct edges in this path, right? So then you play a bit with it. You look at n and what goes to 0 and what does not. And in the end, a condition to have a non-zero limit is that the number of edges in this walk is the number of vertices minus 1. So because the walk spans a connected trees, it has to be a connected graphs, it has to be a tree. In particular, if you walk on a tree, the length of your walk has to be even to start and end at the same point, which means that the odd moments are going to 0. Another way to look at it that Martin told me the other day, and also Justin Salles has a paper on it, is that if you look in the sparse case at the local limit of your graph, you see a tree. So here we also see only trees. Okay, and in the end, when we gather the information, we see that the 2/11 moment of the limit law is linked to the number of tree walks. So M is going to be the number of vertices and 2L the length of the walk. In this very nice way here. It's very nice because, I mean, it's already a generating function, kind of. So just to insist on the definition of tree walks, starts with a complete graph. So here, 4 vertices. Fix a point, here it's 3, and then we do a walk on it. So 1, we go to 4, 2, we go to 1, we come back, we go to 2, we come back, 6, we go to 1, 7, we come back, 8, we come back. So that's a walk. And we want it to end where it started, to visit every vertex, and to span a tree. That's a tree walk for us. Other people have considered walks on infinite trees, but that's unrelated. So, okay, every edge has to be traversed at least twice. And in that case, we say that it is a simple edge. The excess, so the excess of an edge is, yes, if it's traversed 2k times, it's k minus 1, so it's 0 for simple edges. The excess of the walk is going to be the sum of the excess of these edges, which is half the length minus the number of edges. This notion of excess is going to be very important for us in the rest of the talk. So, for example, if you look at 3 walks of excess 0, that's just a walk that we just, we walk on it. Well, our 3 are labeled, rooted, but they are not embedded on the plane, right? At first. But when we walk on them, the order in which we visit the vertices, the children, it orders them. So this gives us a unique embedding in the case of excess 0. So actually, 3 walks of excess 0, that corresponds to Catalan trees plus labelings on the vertices. Because of that, the exponential generating function of 3 walks of excess 0 is equal to the ordinary generating functions of, well, Catalan numbers. So, okay, now we introduce generating functions. We have to. That's the law here. So capital W is going to be the generating function for all my 3 walks, V marking my vertices, and Z my half length of the walk. And I extract a W psi for the walks of excess psi. Those 2 generating functions are linked to the ordinary moment generating function, defined like that. And here we see really why the excess is a good idea to introduce this parameter, because we see that it decomposes the generating function with respect to powers of C, which is what we are after, right? We want the smallest power to understand them. So there was a conjecture on the shape of those generating functions here. So 3 walks of a given excess. And indeed, we prove it. It is that it's a rational function in Z C squared, C being the generating function of Catalan numbers. So how do we prove that? Well, we exactly follow a proof from Wright for connected graphs. The idea is to reduce our walks. So how do we do that? We look at every simple edge. So here, in red, we have the edge with positive excess, and in black, the simple edges. So we remove every leaf that is connected to the rest just by a simple edge, excess 0, and that doesn't change the excess of the walk, right? So we do that again and again, which implies that we have 3 walks of excess 0 that are removed, hanging around. And after we have done that, we also look at the root. And if the root has only 1 edge going out, which is a simple edge, we remove this edge, we put the root up, and we repeat that if necessary. So doing that leads us to the second graph here. And here we still have to reduce. How we reduce? We merge any 2 simple edges that share a vertex of degree 2. We merge them into 1 simple edge. And finally, we reach graphs that we call 3 walks that we call kernel walks. So why do we do that? What are the nice properties it has? Well, the excess is conserved during this process. And also for a given excess psi, the number of kernel walks of this excess is finite. So the reason is that every leaf has to be on excess edge, so there can be at most psi leaves in this tree. And yes, with this kind of reasoning, we arrive at the conclusion that it's indeed finite. Because it's finite, the generating function is a polynomial. And this transformation we made, we know how to reverse it from a generating function perspective and to arrive at the conclusion that at an expression for the generating function of all 3 walks of excess psi using this polynomial, and so we get the expression we wanted. So the next natural question is, how can we express those polynomials k psi? So in order to do that, we reduce again, but I will have to skip the explanation of what is going on here for time reasons. We reduce again, and then there is an idea that we rediscovered, and then we found out that Bauer and Golinelli already had it. They didn't apply it to the same tree walks family, but it's the same idea. So when counting tree walks, there is something that looks a bit, at first, difficult. Is the fact that when we count trees, what we like about counting trees is that the children are independent. And it's not the case in a tree walk. If you go start at the root, go left, visit a bit the left child, come back, visit the right child, come back, and go again on the left, then you have to remember things about the left. Otherwise, it wouldn't be correct, right? So how to handle that? And the answer is that we need an extra parameter to keep track of it, a catalytic variable, which is how many times we leave the root. That's the important information. So, yes, that doesn't work. So when you know this information, you can then, when you have all your children, and you can, from the root, you can decide when you go on the left, do a loop, come back, do maybe another loop somewhere else, come back, and when you go back on the left, you continue the walk on the left tree. And you know how many loops you can do on those trees because you have this extra parameter marked. Okay, so to summarize, we know how to count super reduced trees given the previous recurrence. So we know how to count kernel trees and kernel walks, and then we know how to count tree walks of a given XS. And indeed, we can compute them, concretely, just rational function in C squared. So we get more of them than was known before. That's something. And yes, in the last 5 minutes, I'd like to talk about something interesting about a combinatorial surprise we had. So recall that when you look at the ordinary moment generating function and extract the coefficient in C, you get a rational function in C squared. But if we divide by just the right polynomial in 1 over C and extract the coefficients, if we choose P just right, we can have polynomials in C squared instead of rational functions. And if you take P of larger degree, we believe that you can, so this is true only for the first coefficients up to the same order as the degree of P. So if you increase P, maybe you get more coefficients that are polynomials, and after that, the coefficients are again rational functions. And this is not something that you can do for any sequence. And indeed, if you change the value of one of the W psi a bit, then you cannot build this polynomial P anymore, it fails. So there is some kind of combinatorial miracle here that needs to be explained. We don't have the explanation. We just observe that when we put the numbers in, yes, we can compute always increase the degree of the polynomial P, and it still works. So that's curious, but why does that matter? Is should be a question. And the reason is that it has a clear implication for the empirical spectral distribution. So if we look at the different empirical spectral distribution, it's different because here, instead of just dividing by square root of C, we divide by square root of C multiplied by P of 1 over C. So P is in there. For this new guy, when we look at the moments, well, they are the same as the moments of very nice distributions plus an error term. And here we go up to order 5 because that's how much we computed of the coefficients of P, but of course, someone could compute more, and we believe there is no end to this process. So sigma here is the semicircle law. And the other sigma that we have, in the error terms, there are sign measures with mass, total mass 0. we have explicit densities for them. I will show them to you. So probably what is true is that when we integrate a function phi, a nice function phi, on this limit distribution mu c tilde, it's the same as integrating it against those nice measures plus an error term. So we don't know this mu c tilde, but we can approximate it, maybe. And it feels like an asymptotic expansion in the sense that we believe that the polynomial p, if you add more and more and more terms, in the end, it will be a series with zero radius of convergence. So here are the densities, just to show you what they look like. They all look like symmetrical law multiplied by some polynomial in front. So yeah, just so you know, it's actually computable. And here are some plots to show that indeed, when we consider more sigmas, this improves the prediction matches the empirical distribution better and better. So, yep, that's it. Thank you very much.
Thank you. Okay, so when Wright did this approach for the graph, you had some generating functions which were polynomial divided by 1 minus t to the 3m, t being the Cayley function. So if you do the same in your case, so the numerators will be polynomials, is there a link between a possible recurrence that they will satisfy and the original recurrence of Wright? Do they have a similar shape or?
That's a good question. So in the case of Wright, those polynomials, they satisfy a recurrence with differential equations in them. That is quite terrible. Today, now we know how to express those polynomials directly. We don't need the recurrence anymore. But for a long time, that was the only way to go. And so when people wanted to get the asymptotics of connected graphs with large excess, they had to struggle with those polynomials. It was terrible. Here, I don't know. That's a good question. The way we express those polynomials, those guys here, is through first a reduction, and then, more importantly, this recurrence. So maybe we could derive here and find a recurrence on the derivatives of this guy. I don't know. But there is here a Laplace transform, which makes, analysis strange. So we are kind of in the same pickle as Wright, in the sense that we know those polynomials exist, but computing them is very challenging. And if we knew how to compute them in a different way, maybe we could understand this miracle I was talking about. But we don't yet have the understanding to do that.
Mm-hmm. And at the beginning, you mentioned you were doing the limit in n, taking the first asymptotic term, and then doing the limit in c. Here there is one possible difficulty, which is that when in the initial asymptotic in n, the full next asymptotic terms are also involving c, and perhaps the sum of these contributions that you don't to keep after, they could perhaps contribute to the asymptotics in C in your next asymptotics. So do you have a way to handle this or?
So we really looked at mu c, the limit as n goes to infinity, forgetting all the error terms after that. So what you're suggesting is
you need some type of uniformity to be sure that it will work.
Yeah, exactly. So let n and c move together, kind of. So I haven't thought about that. I thought about the Wigner, in the Wigner case, could we get more error terms? And I think we could with the same kind of ideas. So what you're talking about is, yes, a mix. So if you know how fast one c and n are, moving together, probably we could think about mixing the two. I have no idea of the kind of result or the meaning for the limit empirical distribution it would mean. But that's an interesting idea.
I have a question because this is in fact, I also see this kind of tree walks in another context for another example of random matrices. And I would like to ask, can you, with your method, can you do excess that is variable that tends to infinity along with n as some function?
So no, short answer is no. And the reason is linked to the fact that for the super reduced trees here, the expression we have, there is this Laplace transform in there.
Mm-hmm.
That makes analysis, maybe not impossible, but challenging, let's say.
Okay.
So for fixed excess, yes, we have rational
yes,
functions.
it's
You can
rational
do
in
asymptotics very easily. But large excess, that's a challenge. And I would think that solving that challenge somehow would help for the other combinatorial miracle we have. That maybe the two are linked, and when we understand one, the other will follow. That's my hope.
Okay, thank you very much.